Hello and welcome back to Calculus 1, section 2.6, Continuity, Part 2. Now we discussed the basics of continuity, continuity at the point where it satisfies these three rules, right? So function value has to exist, the limit must exist, and both of those values have to be the same value, so we have continuity at the point. If any of those three conditions is not met, function is discontinuous at the point. And we have the three cases where either number 1, number 2, or number 3, rule number 3 fails. Global continuity is defined when a function is continuous at every point of its domain. And we can also talk about the piecewise continuity. If you have a discontinuity somewhere at the function, well, you will also have a continuous pieces. So, for instance, this function 1 over x would have these two continuous pieces, which we'll call piecewise continuous. That will be important later. Now, since it's well, it's not very tedious, it's impossible to check every point, right, for continuity at the point. To claim global continuity, we have a theorem which states that all polynomial functions, exponential, logarithmic, radical, not rational, radical function, and then sine, cosine, inverse trig, are all continuous on their domain. So now, if you see a polynomial function, you can immediately claim that polynomial function is continuous because of the theorem which we had. If you see exponential function, it is automatically continuous, logarithmic, and so on, each one on their own domain. But then we run into a problem of composite functions. So what happens if I add two functions? If I subtract, multiply, divide, multiply by a constant, or square a function. So there are many ways to combine functions because, function ultimately gives you a number, y equals 3 or something. So output of a function is a number. If you can add numbers, you can add functions that generate those numbers. So what happens with the continuity in that case? Well, that's a completely new theorem, which states that if functions f and g are continuous to begin with, right, on their domain, then their combinations will be continuous as a result. So another theorem this is called continuity rules. Continuity rules. So if f and g are both continuous on their domains, then combinations, or maybe following combinations, how about that? Following combinations of f and g are also continuous on the combined domain. We have f plus g, f minus g, f times g, f divided by g, with g not being 0, f squared, well, no, just call it f to the n. There we go. So 5 properties. Oh, multiplication by a constant. So let's put CF and f to the n. I'll put black commas to separate these. So these are function combinations. You can add functions, divide functions, you can square it, you can put to the 10th power, whatever. So all of these will produce continuous function. Now, we need to be just a little bit careful with the domain issues. Other than that, we should be okay. For instance, if you have that f of x is equal to x squared plus 3, we know that's continuous on entire set of real numbers. So it's continuous everywhere because it's a polynomial. It's a theorem that we covered yesterday. And then g of x is, let's say, square root of x. Now, that is continuous on 0 to infinity because the domain of square root of x is 0 to infinity. Now, if I want to create any of these combinations from above using these two functions, I will have to claim continuity on the most restrictive domain once you combine these. So if I have f plus g, well, in this case, that will be x squared plus 3 plus root x. The domain for this, if you remember your pre-calculus at all, is 0 to infinity. Right? The most restrictive domain is the domain for the entire new function. So, and the theorem that we just covered claims that this function combination will be continuous on this combined domain. So if you have two functions given with the different domains, you have to pick the most restrictive domain and then work it out. You can't pick the bigger domain because if you pick bigger domain, which is all real numbers, then you might want to compute this at -7. But you can't take the square root of -7 and get the real value. So that will be an issue, right? So you have to take the most restrictive domain, and that most restrictive domain is the one that governs everything. But sometimes we have interesting things happen. For instance, in this particular problem, we go with f over g. Right? F over g would be x squared plus 3 divided by square root of x. Domain for the polynomial is all real numbers. Domain for the square root is 0 to infinity with 0 including. What is the domain here? Exactly, not including 0. So see, domain is now even smaller. We kicked out 0 because your denominator is not allowed to be 0. Now, by the theorem above, this function combination is still continuous, but we had to kick out additional point. We had to kick out 0. Now, if I am to flip this and write it as g over f, which is square root x over x squared plus 3, the domain on this one is still including 0, right? Because in this particular case, denominator can never be 0, right? Because any number squared is always positive and you add 3. So there is no way you can get to 0 in the denominator. And in the numerator, you have a more restrictive domain. So that domain becomes the domain of the whole thing. So you have to be a little bit careful when you are combining these functions. Also, there is a way to get rid of this restricted domain. How about we just say, all right, let's do f plus g squared, right? That would actually kill the square root, and then the domain becomes all real numbers. So in that case, we have x squared plus 3 plus square root of x squared. And this is just x squared plus x plus 3, which is the polynomial whose domain is all real numbers. So you know, this is a direct continuation of one of the most important sections from chapter 1 in your pre-calculus course, where you learned how to combine functions. At RVCC, that is section 1.7. So those of you who like to review things or want to see what that important section is, for calculus, if you go to tutoring center or library, there are books on reserve which we currently use for pre-calculus. There's a chili pepper on the cover page by Blitzer. Sections 1.6 for graphing, 1.7 for this stuff and function composition, and then 1.8 for inverse. These three sections will be referenced all the time in Calculus 1, 2, 3, and because they cover the most basic ideas of functions, properties, and important things about functions. So if you need to review those, you can take a look at those books for free at bookstore, not the bookstore, library, and the bookstore you have to pay for the book to review. Library and the tutoring center. The next theorem says that function composition of two continuous functions is continuous. Function composition, which is f of g of x, right? Of two continuous functions, f and g, is continuous. So, if I have that f of x is given as, let's say, x squared plus 3 as before, and g of x is equal to sine x minus 7, whatever, then f composed with g of x, which is actually f of g of x, is also continuous. So we are going to replace x squared. We are replacing x with sine x minus 7, everything squared, plus 3. You can work out this algebra to get sine squared x minus 14 sine x plus 49 plus 3 is 52. And this would be continuous. Now, you also see the piece over here which says sine squared. Well, that is also function composition between sine x and x squared. Sine x is continuous by the theorem from before. X squared is polynomial, therefore continuous. Function composition in there is continuous. So, right, this is like a nested problem for continuity. So this is something that it's very important. I want to actually find, let me see if I can find it on the other computer, use for this. You absolutely must know, if you're going to Calc 2, you must know this. You must know every single of these theorems because stuff is coming up. Let me see if I can quickly convince you of that. So I'm going to look for, you can go on my channel and find the full lectures on this stuff, but I should be able to find maybe in here, huh? Great. Let's see. Not bad. Okay, so this is a lecture in Calculus 2 on divergence test, integral test, and P-series. It's in Chapter 8. I already told you that the Calculus 2, half of the Calculus 2 is integration, the other half is limits, and then derivatives are sprinkled throughout. So when you are, well, you will be learning this, but observe that every single problem has a limit, and that's the entire Chapter 8 and 9. As we go down, here's the integral test, and here are the conditions for integral test. In order for you to use the integral test, functions that you are getting must be continuous, right? And then, is it continuous? Over here, we just skimmed through it because we know the graph. So we said, yes, it's continuous because piecewise continuity, I talked about it. I didn't write it, but I talked about it because the piecewise continuity, we were interested only at the domain 1 to infinity. The discontinuity for 1 over x is at 0. So the piece that we needed, which is outlined in red, is the one that we needed. So we said continuous. Cool. Right? And then the proofs for other two, and then we can actually do the problem. So what you see here in writing, so all of this black writing up to the integral here is preliminary work so that you can start doing the problem. And then you do the problem, and in red, you write the answer. Then you move to the next problem. Now look at that problem. You have to prove that this function here is continuous. And that's standard Calc 2 stuff. So what we learned today is actually going to be this paragraph here. Some answers in calculus are actually paragraphs, writing. So is it continuous? X plus 10 is a polynomial, therefore continuous. Cube root of x is continuous function, also because it's a radical, also on our list, right? Radical functions, that's the composition of two continuous functions is continuous because we are composing x plus 10 with cube root of x. So when you compose those, you get a continuous function. And then we have, since that cannot be 0, right, because it's different than 0, because we are on a domain 1 to infinity, then we are not creating discontinuity also with a vertical asymptote. Therefore, the whole thing is continuous on that interval. This is the way that you are going to combine all of the theorems that you've seen in a continuity, like the last three theorems you've seen in a continuity part, to actually start setting up your Calculus 2 problems. Then you go with the positive, you go with the decreasing, and then finally, in purple, you can solve the problem. Oh, sorry, not in purple, in black, you can solve the problem and give the answer to that problem in red. So that's the standard stuff. And every time, it's going to be the same thing. This is now P-series, which is a different thing. So, combinations of these three theorems, globally continuous, continuity rules, and composition of functions will be what you guys will be using to set up problems in your future courses. Obviously, if you are here to just survive Calc 1 and not worry about any further courses, then you just survive the exam and you're good to go, right? That's that. At this point, continuity is over. I just need to take a look at some examples so that we can inverse, continuity of inverse functions. So that's the last one. if, so inverse, let me put it this way, theorem, continuity of inverse functions. If a function f is continuous on an interval I and has an inverse on same interval I, then its inverse f minus 1, right, is also continuous. Now, if you are reading the book, you have to be very careful with Theorem 215, because Theorem 215 is very poorly worded over there. The following functions are continuous at all points in their domains. And then there's tangent x over there. Tangent x has a vertical asymptote at every pi over 2, 3 pi over 2, right? So you have to be a little bit careful about that. I agree with everything other than these 4, right? Because they have vertical asymptotes. Now, if you kick those vertical asymptotes, right, you have a piecewise continuity for each piece. Yeah, cool, right? But they're not globally continuous. You have to be very careful about that. Also, if you pick what we call a restricted domain, which you can, and just look at the principal domain for tangent, that would be negative pi over 2 to pi over 2, yes, it's continuous. And that principal domain is used to create the inverse tangent, which has the domain of negative infinity to positive infinity, which is globally continuous anyway. So these are fine. All of these are fine. These are fine. And these ones over here, be very careful with that, right? Because there's a difference between globally continuous and piecewise continuous as you go along. So that's that. And finally, intermediate value theorem. So we are done with continuity. Now we have the intermediate value theorem, and the lecture is over. Well, no, we have examples, but lecture part is over. The intermediate value theorem. Okay, let's first write the statement and then we'll see what it means. Suppose f is continuous on interval AB inclusive, right? So closed interval. And L is a number strictly between f of A and f of B. Then there exists at least one number C in open interval AB satisfying f of c equals L. I don't know how much this means to you at all, but what this actually says is that we can solve equations. Now that is a basic building block of everything that exists around us. You pick, it will have some kind of equation somewhere. And if you are to solve that equation, this is in effect. So it doesn't matter the discipline, right? So just it's like a human endeavor, the entire thing that exists, all right? Now, we don't use this directly in the form that it's written, and its meaning is very simple, but it leads to solving equations. So the meaning of this statement is you have some kind of a continuous function f of x in your coordinate system xy as you know, and then you have the interval a to b on x-axis. Now, that interval AB on x-axis is going to create immediately f of a when you compute a in the function, and f of b when you compute b. So if the function is continuous, then if you pick any L between f of a and f of b, that L is guaranteed to be produced by one or more numbers between a and b. And you can trace it back. So this would be that C that produces L. So you pick an interval from A to B. You pick an interval from A to B, and then you have immediately f of A and f of B, because they are produced by plugging in numbers. Let's say A and B is 3 and 4, right? So you will have f of 3 and f of 4, whatever that is. Then you pick a number between those, number L. That number is produced by two numbers that are between A and B. Now, why is this important? Well, equations. First of all, you have to know that not every equation can be solved by algebra means which you know. We have a whole bunch of equations that exist. For instance, there is an equation x plus 2 equals 5. Sure, minus 2 both sides, x is 3, move on. There is equation x squared minus 1 equals 0. Okay, fine. Factor set equal to 0, positive and negative 1. There is equation sine x equals 0. There is e to the x plus 3 equals to 6, right? All of these you can solve by hand. But then, even, right, log base 2 of x is equal to whatever, 9, whatever, right? So you can solve these equations using algebra. But then you have an equation like this. Log base 3 of x is equal to x minus 6. You can just cry over there. You can't use any algebra to solve that. There are some advanced Calculus 2 techniques you can do, but nothing that you learned so far will work on that unless you graph it and you find the intersection point. Or you use this, actually. I'll show you briefly how to use that stuff. Another example would be, let's say, e to the x is equal to x squared plus 6. well, 6 again. Let's use 9, whatever. That's another one that cannot be solved. Because as soon as you ln this side to free up x, you bury the other sign within ln. And then you e the other side to free up, and then you bury the x on the left, right? There is no way to keep both x's free on either of the two equations. They cannot be solved by algebra. And the way to solve the equation would be to graph both sides and to see where the intersection is the most precise you can. Or use what I have up there, or use Calculus 2 stuff that you will learn in Chapter 9. Now, to solve any equation, method that works 100% of the time, but it's very tedious and inaccurate, is graphing. You've seen my x plus 2 equals 5. You can solve this graphically because you have two functions. There is a function on the left, linear line, that you can graph, and a constant line on the other side that you can graph. They will intersect at x equals 3, because they have to. Right? That's the meaning of the statement, graphical meaning of the statement. So if I graph x plus 2, I'm getting a 45-degree line through 2. And then I graph constant line. So this one is y equal x plus 2, and this one is y equals to 5. They intersect at this point. At that point is 3. X equals 3. That's the meaning of equations. So any equation, I don't care whether it's trigonometric, exponential, whatever exists in the universe regarding equations, you graph the left side, you graph the right side, and whenever they intersect. If they don't intersect, there is no solution. And that's possible too. You know how many times you solved a problem here and there and it said no solution. Fine, no solution, and that's it. So now, how do this intermediate value theorem can be used to, so intermediate value theorem can be used to find the solution to the equation. Because observe what the solution to the equation is. It's the intersection of two functions. So if you have some kind of evil function to deal with, like e to the x equals x, e to the x equals x, that's it. You will move everything to the left and make it equal to 0. And then, whatever this looks like, it has to cut x-axis somewhere. All right? Has to cut x-axis somewhere. So whatever it looks like, I'm just going to put arbitrary f of x. This is nothing close to this, but I'm just going to put arbitrary f of x. Look at a cool thing. This is going to be your solution for the function, x equals 3.1, whatever, right? So that's the solution to the function. Observe what's happening with f of a and f of b. If this is your a and this is your b. See, f of a and f of b always have opposite sign. One is negative, one is positive, if the solution is trapped in between. So you can keep zooming in, guessing the interval on which your point is. Eventually, your partitioning will be so smooth and so small, not smooth, small, that you will start getting the digits, the correct digits for your answer. So we can, we'll discuss this more in the future, but it's a really interesting thing. We never use this because it's labor intensive, right? We have calculators and computers to tell us the solution right away, but you know, some of the algorithms might use this. So yeah, it's cool stuff. The way it works, and then we'll switch to the next thing. The way it works is, say you have equation which says x squared minus 3 equals to 0. Let's say this is your equation. So you want to find roots for this. Well, you know how to graph this because it is just x squared and vertex is at -3. Now, you pick the interval over here around the root. You don't know what the root is, but you kind of roughly know that that 1, right, is too small, right? The 1 is too small for an answer, and 2 is too big for an answer. You know that much, because if you plug in 1, you get -2, which is not 0. And if you plug in 2, you get 1, which is also not 0. So you guess the region in which you believe the answer is. And then when you try, so you are guessing 1 to 2. And when you try now f of 1 is going to give you 1 squared minus 3, which is -2. And f of 2, which is the other end, is going to be 2 squared minus 3, which is +1. So when you have this, you see that 1 is negative, 1 is positive, and by the theorem that we just have, right, the theorem we just had, intermediate value theorem, the solution is, which is 0, is in between these two numbers, right, because you are looking to find where that y equals 0 is. So there has to be, right, in between. So what you have to do now is to keep guessing numbers and making the interval smaller to squeeze it. Now, by the way, you already started with your solution is x point something, right? Because all of the numbers between 1 and 2 are 1 point something. You know, 1.537, all right? 1.537. So you already know that your solution is 1 point something. So now you want to zoom in more. So you say, all right, let me try to go from 1 to 1.5. You cut the interval in half. You calculate f of 1, which you know it's -2, and you calculate 1.5. Right? That's a 225, no. 225 minus 3. See? So this is bad now. You see that? You have two negative numbers. 225 minus 0.75, right? So I have to put two x's here because both are negative. But because both of these are bad, that means that the solution can't be here. It has to be in the other interval, which is 1.5 to 2. Right? If it's not here, so I'll put, I don't know how to, oh, okay. Answer is not in this interval. So you switch the interval from 1.5 to 2, but you know it's already in there, so you can make it smaller. So how about you go from, I don't know, 1.7 to 2. Now you can do 1.75, whatever. Let's do 1.75. That's half of the interval. So 1.75. Now use your abacus to compute again. F of 1.75. Anytime you get same signs, you have to go to the other interval. Every time you get the opposite signs, that means the answer is still within those two numbers you guessed. So what do we have? Let's see. My function is x squared minus 3. So 1.75 squared minus 3 is 0.625. And f of 2, guys, was 3. That's not good, right? Both of these numbers are positive, right? So answer is not in there. So answer must be between 1.5 and 1.75. So answer is in this region. So now you pick a number in there. So let's say you pick, well, let me just see. Okay, for 1.5 to 2. There we go. So now you pick, let's say, I don't know, 1.7 to 1.75. So now you compute f of 1.7. You see, you're guessing the answer, but eventually you guess the next digit and the next digit. So if this works, and a spoiler, it will, the next one is still cutting the interval now with 2 decimals and 3 decimals, and you can keep the precision as far as you want, as far as you want to keep computing this, guessing and computing. So 1.7 squared minus 3 is negative 0.11, and f of 1.75 was positive 0.625. You see, 1 is less than 0, 1 is more than 0. I mean, 1 is positive, 1 is negative. So yeah, that's good. But look what you have. You have that the number that you are looking for is between 1.7 and 1.75. You just discovered another digit for your answer, because it must be 1.7. Now is the time to cut this interval in half. So let's try 1.73 to 1.75. You try this. 1.73. Again, you compute 1.73. You are looking for positive, negative. You keep cutting the ones that are positive and negative. You keep rejecting those that are either both positive or both negative. With this method, you can go to whatever amount of decimal values you want. Calculator is going to give you 5 decimal, 6 decimal, 12 decimal, right? With this method, you can sit there for, 27 years and compute to whatever decimal precision you want. I just have to be focused enough to do that. 7.3 squared minus 3 is negative. Okay, so f of 1.73 is negative 0.0071, and f of 1.75, we are still recycling this one, 0.625. This interval is good. You can cut it in half if you use 7.4. Now, you don't know if you are going to use 7.4 on a first or a second, but it doesn't matter. Pick any. If you get same values, reject it, use the other one, and that immediately gives you the next digit. Next calculation has to give you next digit. So let's go with 173, and this is where I'm going to stop. 174. So we need f of 1.73. We know that's negative 0.0071. That's the same as before. I need a new calculation for 7.4. So 1.74 squared minus 3 is positive. Yes. 1 is negative, 1 is positive. It's a good interval. But that gave me the next digit, 1.73. So now what do? You go with the third decimal, 1.73524. And you keep cutting that one, and you keep cutting the next one. You keep cutting. Every time you zoom in on a digit, you add a digit over there. And you can go indefinitely with this method. Obviously, if the answer is finite number, then you stop. But, in this case, the answer is square root of 3. Right? If you solve that equation, which you should be able to solve, right? And you know that the decimals of, the first 2 decimals of square root of 3 are 1.73. So that will go there. So that's the intermediate value theorem. I believe you have one lab question on it, or maybe 2, to play with the intervals like this. As I said, we have calculators, computers to take care of this stuff today, so we actually don't do this by hand. But at some point, in human development, people had to do this. So, yeah. All right, let's restart for the last section.